Alrighty then. This short video will just bring to your attention how we can use stoichiometry to determine enthalpies, changes in enthalpy, and we use our thermochemical equations we looked at in the last video, and we use our prior knowledge of stoichiometry, one of my personal favorite topics. So let's get stuck right into that. Okay, so you remember stoichiometry from last year and the fact that stoichiometry involves balanced chemical equations. So there's our equation: 2 moles of aluminum reacting with 3 moles of chlorine to produce 2 moles of aluminum chloride. And now we have our enthalpy term as part of that equation. That's why it's known as the thermochemical equation. And in this case, we know that the reaction is, that's right. So here's the question: what would be the enthalpy change if aluminum chloride is produced from a reaction between 16 moles of chlorine and excess aluminum? And so it's really no different from any other stoichiometry problem. We have to use a mole relationship, but we're given, in this case, because of the question, we're given 1 molar amount, and we're going to use the other molar amount. So the other molar amount is the molar amount of chlorine in our balanced equation. So let's set that up. We're looking for an enthalpy of reaction, so delta H Rxn. We're given our standard enthalpy of reaction, that's negative 1408, and we're going to multiply it by, basically, it's not really an equation, it's not really an equation factor, it's actually a mole ratio. But the mole ratio does come from one of the components of the equation. So our standard enthalpy of formation of reaction is negative 1408 kilojoules. Don't forget the sign; it's critical in thermodynamics. And so our ratio is moles of aluminum in our reaction. Sorry, moles of chlorine in our reaction, 3 moles of Cl, and moles of chlorine we have. Now, before we come up with this ratio, we just need to remember that that enthalpy of reaction, 1408 kilojoules. Well, if 2 moles of aluminum react, that's the amount of energy released, the heat energy released. If 3 moles of chlorine react, we release that much energy. If 2 moles of aluminum chloride is produced, that's the amount of heat energy produced. So that enthalpy relates to the molar amounts given in the equation. Well, we have 16 moles of chlorine. So if you react 16 moles of chlorine, clearly we're going to produce more than that. The amount of energy or heat energy is going to be greater because we are utilizing more chlorine. And so it's really easy to get these ratios. It's just 16 moles over 3 moles. The amount of energy will be larger because we have more moles than we show in our balanced equation that gives us our standard enthalpy of reaction. And so when we do the math on that one, we get negative 7,509. And again, that makes sense because we're reacting 16 moles of chlorine, not 2 or not 3. 3 moles of chlorine yield 1408 kilojoules of energy. 16 moles must yield more. Let's look at another example. What's the enthalpy change when 1 kilogram of aluminum reacts completely with excess chlorine gas? Now, we have the same equation, but in this case, we're given a mass. And so, just like last year, the first thing we have to do is convert our mass to a number of moles. Now, for that, you need the molar mass of aluminum, and that is equal to 26.98 grams per mole. And so our first step is to determine number of moles of aluminum. Mass divided by molar mass, 1 kilogram, which is converted to grams, divided by 26.98 grams per mole. So kilogram, forgot the unit there. Kilograms are gone, grams are gone, and we're left with a molar amount of 37.1 moles of aluminum. So 37.1 moles of aluminum are reacting with excess chlorine. And so back to our calculation, we're looking for an enthalpy of reaction, and that equals our standard enthalpy of reaction that we're given, multiplied by this ratio. And again, the molar amount of aluminum is much higher than the amount in the standard enthalpy of reaction equation, so it's going to be 37.1 moles divided by 2 moles. Moles divide out, and in this particular example, we yield 5.2 times 10 squared, or 10 to the 4th kilojoules. So again, it should make sense. The molar amount in our reaction is far greater than the standard amount, and so we should produce more kilojoules. One last example. What about if it's phrased this way? What mass of water can be boiled but expending 120.75 kilojoules of energy? Well, there's the enthalpy of vaporization. So remember what enthalpy of vaporization infers. It's the amount of energy required to cause a phase change between substances. And so the phase change for water is from a liquid to gas if it's vaporization. And so in this particular case, we're sort of coming at it from the other side. But again, we're given a mass of water, or sorry, we're asked for a mass of water. So if we're asked for a mass, just like I told you last year, you should always consider that you're going to have to use the molar mass at some stage. So the molar mass of water, 18.02 grams per mole. Now, delta H of vaporization equals the enthalpy of a reaction divided by the molar amount, kilojoules per mole. And so we're looking for that molar amount. So N equals an enthalpy of reaction, which we know, divided by the delta H of vaporization, which we know. So that is 120.75 kilojoules divided by 40.7 kilojoules per mole. And so when we plug that into our calculator, we get 2.9668 moles. And now we just convert moles to a mass. Mass equals number of moles times molar mass. 2.9668 moles times 18.02 grams per mole. And the math there tells us we would boil. We would be able to boil a mass of 53.462 grams of water. 53.462 grams of water. Well, how much is that? Well, there's a 100 millimeter graduated cylinder, so a little more than half full of water. Now, you know, that number, again, may be kind of irrelevant, 120.75 kilojoules. Just to put it into a bit of context, that is equivalent to roughly, this number is equivalent roughly to about 12,000 calories. And again, to put it into context for me, when I run about 10 kilometers, I expend about 1,100 calories. So, you know, another 10 times that amount just to boil 53 milliliters of water. So, kind of indicates or demonstrates the strength of those hydrogen bonds, that intermolecular force between water molecules. That's a pretty strong force if it requires that much energy to change them, or to vaporize that sample of water. And that concludes this video.